So what are these orbitals like? Well, we specify the orbitals with a number and a letter. In the Bohr model, the orbits were just 1, 2, 3, etc. Here, we still have those numbers. We call them principal quantum numbers, and it's still an N. And that specifies the principal shell, or the sort of a general energy level of those orbitals. As N gets bigger, the energy level of the orbital increases. So if N is 3, an electron in that principal energy shell has more energy than one in level 1. And we also use a letter. The letter indicates a subshell because within that shell there are subshells, sublevels. And the letter indicates the shape of the orbital. The letters are S, P, D, and F. You may wonder, why did they choose those? I can never remember what S is, and I can't even remember to look up what S is. But P stood for principal, and D stood for diffuse, and F stood for fine, and these related to descriptions of the emission spectrum of an atom. And so the letters are not random, they did come from somewhere, just in case you were wondering. So one of the orbitals is the 1s, principal energy level 1, and it's subshell S. That's the lowest energy orbital. Now orbitals are three-dimensional. They're not like the circular orbits, but they're three-dimensional. And one way to represent them is with a dot representation, which is a little bit like the picture I drew of Andrew. So imagine taking a photograph of an electron every second for 10 minutes, and it would show up here as a blue dot. Now you can't actually do that, but if you could, it would look something like this. And the density of the dots represents the probability of finding the electron in that region. And so we see that overall this has, a spherical shape to it, but that the electron is more likely to be more in the center here, and then the probability falls off here, and then out here the probability is very, very low. And so we see that most of the time the electron is in this region, and that's one way to represent an orbital. We can also think of it as a geometric shape. The s orbitals are spherical, and so we can draw a sphere, and that can represent the volume within which the electron is found 90% of the time. So it's like my house. On a given day, perhaps 90% of the time he's in the house. Or let's say that on the property. And 10% maybe because he does like to go across the street to his friend's house. He looks both ways though. He's gotten pretty good about that. But does the electron have to be inside that sphere? No, it doesn't. What that is we calculated 90% of the time it'll be within that region. But we pretty much expect it to be somewhere else 10% of the time. That sphere is not a container for the electron, okay? That's just our representation of where the electron probably is. Oops. So we can superimpose those, so watch this. See that? Now we've got the dots on top of the sphere. Did you miss it? We'll do it again. So the sphere represents the highest density, the high density part, where 90% of the dots are. So hydrogen has one electron, and in its undisturbed state, that electron is going to be in the lowest energy orbital it can be in. I have two teenagers again. Some of you are still teenagers. Others of you remember being a teenager. I think especially teenage boys tend to gravitate toward low energy states. Zach's favorite position, the most likely place to find him, flat out in bed, messing around with his phone. He's flat. Okay, does he lay in bed all day long? No. He gets excited and gets up and goes and does stuff, but then he always comes back and he's flat out. And if he's not flat out there, he's flat out on the couch, right? Because low energy. Okay, he just runs out of energy. Electrons do the same thing. They're looking for low energy. Water goes to the bottom of the hill. All of nature is about going to lower energy. You want to go to this resting place. So the electrons are going to go to lower energy orbitals. We call that the ground state. That's like normal, low energy. But then something can come in, a bolt of electricity or something, and infuse energy into that electron and cause it to move, to jump to a higher energy orbital. And we call that an excited state. That excited state with the extra energy is unstable. The electron won't stay in that high energy level. Just like Zach doesn't stay up and moving around the house. He always, he'll be up for a while and then he's laying down again. The electron will be excited for a while and it will return to the ground state. When it returns to the ground state, that's when it sends the energy back out. And it's going to be a packet of energy. It's it's photon with a particular energy that corresponds to the difference in the orbitals, the difference in energy in the orbitals. So all atoms have one ground state, one lowest state, but they can have multiple excited states, depending on how much energy came in. That electron can go from n equals 1 to n equals 2, or to n equals 3, or n equals 4. There's multiple states that it could be in an excited state, but only one ground state. So what do those higher energy orbitals look like? Well, the n equals 1 principal shell has one subshell, it's the S, and we already looked at that. N equals 2 has two subshells, S and P. And the 2s orbital looks a lot like the 1s orbital. The difference is it's higher in energy and it's a little bit bigger, but it's exactly the same shape. And the 2p subshell has 3 orbitals, and this is where things start to get a little weird. So here's the dot representation and here's the shape representation. So, that's just kind of a weird shape. Most books refer to it as being shaped like a dumbbell, and I suppose there are dumbbells that are kind of shaped like that. To me, it looks a lot more like 2 balloons. But there's 3 different orbitals. They have the same shape, but they have different orientations, and they all have the same energy. And so this one is lined up along the x-axis in 3-dimensional space. This one is lined up along the y-axis, and this one along the z-axis. So they don't actually overlap with each other. And again, that shape is a region of probability of an electron being there. So there's a pattern going on here. In the first shell, the principal energy level, n equals 1, there's 1 subshell. In n equals 2, there's 2 subshells. In n equals 3, there's 3 subshells. Guess how many subshells in energy level 5? 5 subshells. Okay. Now the letters, S is the first one. So the second level has S and P. The third level has SP and adds D. And the fourth has SP, D, and F. And when you go higher, there's more, but we're not going to go there, and we don't want to go there. Things get really, really crazy. So we looked at S and P. Let's look at D. Let's look at the third energy level first. So n equals 3, the principal shell has 3 subshells, S, P, and D. The S and the P subshells are the same shape as they were in the second level. They're just larger and higher in energy. But then the D subshell is very different. And I'm not going to make you draw these, so don't freak out. But there are 5 d orbitals, and again they kind of look like balloons. But this time they have, most of them have 4 lobes instead of just 2, 4 balloons instead of 2. And again, they're oriented differently in space. And then there's this guy that's really weird. It looks like a p orbital with a hula hoop or a life preserver or something. So those are the shapes of the d orbitals. Electron configurations. So we described the orbitals, and I'm not going to expect a lot out of you in terms of shapes of orbitals and stuff, but that's kind of the background information, the minimum I have to tell you so that you can understand this next part. An electron configuration shows how the electrons are arranged in those orbitals. It shows which orbitals have electrons in them, which ones are occupied, and which ones are not. So in the ground state for hydrogen, I like to start with hydrogen because he's small and easy. So 1s, we already talked about, that's the lowest energy orbital. And so hydrogen's one electron is going to be in that 1s orbital. And so in an electron configuration, we illustrate it this way. We give the name of the orbital, 1s, and then the superscript here tells how many electrons are in it. So this is 1s1, meaning there's one electron in the 1s orbital. Any questions? Another way of representing how electrons are arranged is by an orbital diagram, and this is more of a picture. So if you're more visual, you might like this a little better. Here the electron is represented as an arrow. So here's the electron, it's this pink arrow. And the orbital is represented as a box. So in this orbital, in this box, we have one arrow, one electron in this box, in this orbital. So this is the 1s orbital, and there's one electron in there. Again, that's for hydrogen. And you may wonder, well, why was that arrow pointing up? Well, there's some significance to that. Electrons have something called spin, and it's kind of like right-handed and left-handed electrons, or you could think of tops and one spinning one way and one spinning the other way. It's a characteristic of the electrons. It's a fundamental property of them. And it just works out that orbitals can only have, they can have no more than 2 electrons. You can have empty orbitals, you can have an orbital with 1 electron, or you can have 2 electrons. If you have 2 electrons in the orbital, their spins must be opposite. You can't have 2 electrons in there with the same spin, because they will repel each other. So we have arrows pointing up and arrows pointing down. So in the box, we can have 2 arrows, but one has to point up and one has to point down. I should draw a picture. They had a picture in the slide, but it wasn't very nice. Not that this will be any better. So here's our 1s orbital, and if we have 2 electrons in there, one's pointing up and one's pointing down, because they have opposite spins. What element has 2 electrons?
Helium.
Helium. So this is the orbital diagram for helium, because in the 1s orbital, it's got 2 electrons. Each orbital can hold up to 2 electrons, and the lower energy orbitals are going to fill up before they go to higher energy orbitals. So let's write electron configurations and orbital diagrams for helium and for lithium. Well, I already did the orbital diagram for helium. It's 1s. So that's helium, and down here we'll do lithium. So electron configuration, we give the name of the orbital, it's a number and a letter, and then a superscript to tell how many are in it. So for helium, the orbital is 1s, and it's got a 2. And it looks like 1s squared, but we pronounce it 1s2. So there are 2 electrons in the 1s orbital. How many electrons does lithium have? 3. Lithium has 3 electrons. So there's that 1s orbital. The first energy level, n equals 1, only has 1 subshell. It's got the s. The second energy level has another s orbital, and that's going to be the next highest energy. So here's the 2s orbital. And so lithium has 3 electrons. 2 of them are going to go in that lowest one, and the other one's going to have to go into the higher one. So we would represent this as 1s2 and 2s1. So the 1s orbital has 2 electrons. The 2s orbital has 1 electron. Isn't this fun? Yeah, it's great. Oh, it's awesome. Any questions yet? Yes? S, P, D, and F. No, the lower energy orbitals will fill up first. That's a good question. Why don't you go on to the P? The P orbital is there, but it's vacant. It's empty.
How many of the S do you fill up for?
Well, there's only one of the S in each energy level. And in each energy level, there's 3 P orbitals and 5 D orbitals. 1, 2, 3, 4, 1, 3, 5. And then it goes 7 after that. Let's do calcium. Eventually we will do calcium. We will do all the way up to calcium. But any questions about these little guys first? This is weird, okay? I grant you that. It's weird. So when we have atoms that have more than 1 electron, then the subshells within a principal shell don't have the same energy because of interactions between the electrons. So the first level, n equals 1, that's the lowest energy, and n equals 2 is higher in energy. But we would expect these p orbitals to be the same energy as the s, and yet they're not. They're a little higher in energy. And then the next is 3, because 2 has 2 levels. It's got S and P. 3, principal shell 3, has 3 sublevels, S, P, and D. There's 1 S orbital, there are 3 P orbitals, there are 5 D orbitals. Next is 4S. The 4th principal shell has 4 sublevels. We're not showing all of them. We show the S, P, D, and then there's also F. But we're not going to do anything with those guys. So if you compare the S orbitals, we see that the energy increases as the principal shell number increases, the principal quantum number. 1, 2, 3, 4, 5, energy goes up. Here as we go from 2 to 3 to 4, the energy goes up. Here as we go from 3 to 4, the energy goes up. And yet, the 4s orbital is lower in energy than the 3d level, because the interaction between the electrons causes these orbital energy levels to get skewed. So let's write the electron configuration and orbital diagram for carbon. How many electrons does carbon have? 6. So we've got carbon with 6 electrons. Carbon. I'm going to do the orbital diagram first. So the lowest orbital is the 1s orbital. So I'm going to put 2 electrons in there. That's not a very good electron. And the next one was 2s. And I'll put 2 electrons in there. And the next one was the 2p. But there were 3 orbitals, and so we draw 3 boxes. This is 2p. There's 3 of them. When the electrons go to enter these orbitals, they're going to be in an orbital by themselves if they can. This is a little bit like people getting on a bus. When I was in college, I rode the bus to school. College town and then really nice bus system. You get on the bus, do you go sit next to someone you don't know when there's empty seats? No. People are going to think you're really weird, right? If you get on the bus and there's empty seats, you go take an empty seat. Once all the empty seats are full, someone gets on, then nobody thinks anything about it if you sit next to a stranger, because that's what you do on the bus. But you don't sit next to a stranger unless you have to. So the electrons will do the same thing. If possible, they're going to get an orbital all to themselves. And that's what Hund's rule says. When filling orbitals of equal energy, electrons fill them singly first, and then with parallel spins. So we've accounted for 4 of carbon's electrons, and so we're going to go in like this. So they're going to go in with parallel spins, and they're going to take their own orbital if they can. That's the orbital diagram. The electron configuration, once you've done the orbital diagram, is just counting. So we have the 1s, and there are 2 electrons in there. And we have the 2s, and there's 2 electrons in there. And we have the 2p, and there are 2 electrons in the 2p level. So that's the electron configuration for carbon. 1s2, 2s2, 2p2. That sounds like we're speaking some strange code. Yes?
On the letter, why didn't it go 3S?
And why didn't you go like
Why didn't it go
1P?
1S, 2S?
Why did you skip straight to 3P?
Okay, that's a good question. So I got a question, why didn't you go to 3s? And why didn't you do 1p? Well, let's go back to this picture. So the first principal shell only has 1 subshell. It only has S. There is no 1p. So we can't do 1p. The second level, here's the 2s, that has 2 subshells, S and P. The S subshell is a little lower in energy than the P subshell, but both of these are still lower in energy than the 3s. Okay? Oh, that's a good sound. So this one's going to fill up first, and then this one, and then they're going to go 1, 2, 3. Actually, I'm just going to draw. I'm going to draw on these. Yes. So the lines are one way to represent it. So if you're putting electrons in here, first you'd put 1 here and then here. Whoops. And then 1 here and 1 here. And then when you're putting electrons in here, they're going to go separate first with parallel spins. And then as you add more, they're going to pair up as they have to. Once that level is full, they'll go to the next energy level, which is the S, 3s. They'll fill that one up. The 3p is a little lower than the 4s, and so they'll go fill that one up. Singly first, 1 in each, and then all the bus seats have somebody in them, so you have to sit by a stranger. Okay, and so they're going to go in order like this. And then the 4s kind of snuck in there, but there still is 3d over here. And in the orbital diagram, we would represent this with 5 boxes. So each of these boxes represents one of these lines, but they'd fill separately first.
So you, after 3P, you go to 3D before you go to 4S?
No, you go to 4s first.
Really?
Really? Yeah.
So we just need to memorize this.
Well, there's another table coming up that might help. And then we'll also find out on Thursday that we can see all of this in the periodic table. It's very cool. It's all hidden in the periodic table. It's beautiful. It's incredible. It's a hard thing to teach because it's so weird, but when we get to the end, at least some of you are going to go, wow, that periodic table is the awesomest. Okay, so this might help some of you. That's a nice look you've got on your face there. This is one way. How does this help? That's a good question. Well, it needs a little explaining, which is why you don't just read the book and understand this. So what you can do here is you write these numbers: 1s, 2s, 2p, 3s, 3p, 3d. See, the first level has 1, the second level has 2, the third level has 3, the fourth level has 4, s, p, d, f. And then it fills in this diagonal way. Turn, there we go. So 1s, and then you come up here, 2s, and then you come back up here, 2p, 3s, 3p, 4s, jump up here, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 3d, 6p, 7s, 5f, 6d.
What makes it fill the 4F first, something like that?
It is all to do with the energy levels. They'll fill the lowest energy level one first. And the reason that all the 4 subshells are not higher in energy than all of the 3 subshells is because of interactions between the electrons. It tweaks the energy levels. I know. It's like, really? Couldn't it just be 1, 2, 3, 4, A, B, C, D? No, that would be too simple. So this is one way to remember the order. The other way, like I kind of hinted at, we're going to see on the periodic table. And so I don't do that. I look at the periodic table and it tells me what order they're in. And I will show you how the periodic table can tell you.
Is this picture and that previous picture in the book?
Yes.
Okay.
All the figures in my slides, almost all of them, are pictures in your book. Figures in your book. Yeah. And I did post these on Blackboard as well, the slides. So here's a summary of what we've covered so far. The lower energy orbitals fill before the higher energy orbitals. Okay, so that's why they're going in that order, because that's the order of energy. You know, and I cannot give you a good explanation other than the electrons interact. I can't give you a real satisfactory explanation of why, unless you want to go into molecular orbital theory, which my 1A students last summer didn't like either. So we're not going to go there. You'll just have to take my word for it. Orbitals can hold no more than 2 electrons each. If they have 2 electrons, they have to have opposing spins, and that's known as the Pauli exclusion principle. When you have orbitals of identical energy, so the 3p orbitals in any level, 3p or 4p or 5p, those 3p orbitals are going to be the same energy. When you have ones like that with 5 of the d orbitals, you're going to fill them up singly with parallel spins before you pair them up. So remember, getting on the bus, don't sit by strangers unless you have to, right? People look at you. It was really, and you face the same direction. It's really interesting watching people's behavior on the bus.
Kind of like a train then, because you
Look.
on the train and there's like...
Yeah,
ways.
sort of, yeah. Yeah, exactly. Like a train. I have another example that involves a hotel, but I don't want to record that one because it sounds a little weird. So let's practice here, right? Electron configurations and orbital diagrams for nitrogen, oxygen, fluorine, and neon. Well, let's do nitrogen first. So I'm going to put out the, I guess that's good. So let's do the orbital diagram first. Oh, they're slipping a little bit. Well, it seemed like a good idea. I need to practice doing that. So 1s, 2s, and this is 2p. So nitrogen has how many electrons? 7. So these are the orbitals that are available, and they're going to fill them up lowest energy to highest energy. So 1s is going to, 2 electrons can go in there, and the 2s, we have 2 electrons in there. That's a total of 4 electrons. We've got 3 left, and so they're going to take their own seats on the bus, and that's going to be the orbital diagram for nitrogen. How do we write that as an electron configuration? Well, it's just like shorthand saying what's in the boxes. There's 2 electrons in the 1s box. So 1s2, 2s2, and how many electrons in the 2p? 3. That's the electron configuration for nitrogen and the orbital diagram for nitrogen. What about oxygen? Yeah, oxygen has 1 more electron. So where's that electron going to go? It's going to go over here. All the seats on the bus have 1 person in them, so he has to sit by somebody. And then over here, we have 1s2, 2s2, 2p4. Let's go green for fluorine. Fluorine has 1 more electron, so that electron's going to go in here. So 1s2, 2s2, 2p5. And neon's electron's going to fill that up right there. So neon is 1s2, 2s2, 2p6. The electron configuration for neon represents completely filling the second level. Principal energy level 2, principal shell 2, has 2 subshells, the S and the P, and here they are all filled. Any questions? Yes?
How do we do the orbital diagram when it starts skipping shells?
You just write the correct numbers
In the same
in
order,
there.
so to
Yeah,
speak.
so next will be 3S and 3P, and then you draw the 4S before you draw the 3D. Yeah,
That's all on the work.
right. So there is a little bit of a shorthand. We can use the electron configuration of the previous noble gas. We can abbreviate it by putting the element symbol in brackets. And you're like, what are you talking about? Okay, let's do sodium. Sodium is over here. Okay, it's 1 past neon, right? So neon was, let's write down what neon was. We just did it. 1s2, 2s2, 2p6, right? That's what neon was. So sodium has 1 more. So it's got neon, and what's next?
3s1.
3s1. So that's the electron configuration for sodium, or we can abbreviate it like this. That saves a little bit of writing, huh? Because what we're saying is that it has the electron configuration of neon plus what we write after it. And so for sodium, it's just that 1 electron after it. So that's the, some books call it a noble gas shorthand question.
Could you write helium as H in brackets, since it's 1s1 plus 1s1?
Well, helium is 1s2. If you can use helium in brackets as an abbreviation for like boron or something, it doesn't really shorten it much. Helium in brackets isn't really much shorter than 1s2.
Okay.
But you could, yes. When you get to these bigger ones and you use like argon or krypton in brackets, it saves you a lot of writing.
And so we're always going to be using the far end of the periodic table.
It's always the noble gas, because when you get to the noble gas, the principal energy shell is full.
Okay.
So whoever was at the previous, so like for calcium. For calcium, we just go back to the previous noble gas is argon. So argon would be the, in brackets. Let's just do that over here on the side. So for calcium, calcium would be argon plus 2 electrons, right? Would be calcium, argon plus 4s2. Because, see, this is 3s2, and these are the 3p6 electrons, and this is the 4s2 electrons. These are the 3ds, and those are the 4p's. It's a little preview.
Does the noble gases having an inert or a full shell have anything to do with them?
Does the noble gases being inert and having a full shell, is that at all related?
Yeah.
Absolutely. It is absolutely related. Yep.
The full shell keeps them from being.
Yep. All of the noble gases have a full, what we call valence shell. Their outermost energy level is full of electrons, and it turns out that that is a very, very, very stable configuration. And that's why the noble gases form almost no compounds. They don't burn, they just don't react. And over here, we've got some of the most reactive elements. They're just 1 electron off from being like those. And so they will react in a way to get rid of that electron. And we'll see how that all works. Let's practice writing electron configurations. Let's do aluminum. Electron configurations, not diagrams, electron configurations. So how many electrons does aluminum have? It's got 13 electrons. So we're going to go 1s2, 2s2, 2p6. We've used up, what, 10 electrons there? We need 3 more. After 2p comes 3s, and we can put 2 electrons in there. Now we're at 12. And then we need to go into the next level, which is 3p, and that's going to have 1 electron. When you're first doing this, it probably helps to look at that table with the lines and the energy levels and just fill from the lowest and go up.
Is there any way that we can tell box ratio?
Box ratio.
Like which ones are, I remember how on 2P actually has 3 separate boxes of objects listed in it.
Yes, it's on the periodic table. So over here, this column of the periodic table sticking up, there are 2 boxes, right? 2 squares. That represents the 2 electrons that are in an s orbital. How many p orbitals are there in any level? There's 3, right? How many electrons can they hold? 6. 1, 2, 3, 4, 5, 6. Coincidence? No. How many d orbitals in a given level? 5. They can hold a total of 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, 15. Never mind. I don't like those guys. We don't need to go there. Everything falls apart eventually. We'll ignore those guys. But this block of the periodic table represents the p orbitals. And this block over here represents the s. And this block in the middle represents the d orbitals. And so it's all there. Bromine. Bromine has how many electrons? 35. They're like, ay. Let's use the noble gas shorthand for that one. What's the previous noble gas? Argon. So bromine has 35 electrons. So it's argon plus what? Well, argon, this is the 1s, 2s, 2p, 3s, 3p, and next is 4s2. And then what's next? The 3d orbitals, and that's full. That's not a very good S. 4s2, 3d, 10, and then 4p, and there's 5 in there. And then strontium. We definitely want to use the noble gas shorthand for strontium.
Krypton.
You can use krypton for that. So it's krypton, but plus what? This is where the doing it off the periodic table is so much easier. The first row is 1s, the second period is 2s, 3s, 4s, 5s. So this is krypton plus 5s2. Yes?
Would it be incorrect if you just wrote the whole thing out?
No, it would not. So this one would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. And you can check that by adding up all the superscripts. Strontium has 38 electrons. The superscripts should add up to 38. Any other questions? Here's another example. Let's do an orbital diagram for argon. So let's just start out by drawing some boxes. That would represent 1s, and this is 2s. And then we've got, oops. So let's label these guys. This is 1s and 2s and 2p. And then what do we have next? 3s and 3p, right? 3s